We present polarity sampling, a provable method for controlling the generation quality and diversity for any pre-trained deep generative network. We propose a novel latent space distribution that is controlled by a single parameter called the polarity parameter rho. Polarity sampling allows us to control the distribution on the output manifold of any generative model in a plug-and-play fashion. It allows the user to focus the sampling on the modes, sample uniformly from the output manifold, or sample the anti-modes of the distribution learned by the generative network. Suppose we have a WGAN generator G with leaky ReLU activations. The generator has learned a mapping between latent space Z and output space X, corresponding to the example that we have previously shown. To perform polarity sampling, we start by sampling n latents uniformly from a bounded domain of the latent space. We then evaluate the Jacobian J sub G of the generator at these points and calculate the product of the top k singular values. This gives us a Monte Carlo approximation of the change of volume induced by the nonlinear mapping of the generator. We denote the volume scalars for different latent space points as sigma. It can be clearly seen from the image to the right that the volume scalars are smaller for samples in the modal regions of the output distribution, and they're larger for the anti-modal regions or the sparser regions of the output distribution. To perform polarity sampling, we can resample from the n latents by reweighting the latents based on their volume scalars, or use a rejection sampling criterion to obtain polarized samples. Polarity sampling works for state-of-the-art deep generative networks as well. Consider StyleGAN2 trained on the Elson CATS dataset. The quality and diversity of this generator can be measured via the precision and recall metrics. Compared to standard methods of control, for example, the latent space truncation method for StyleGAN2, the polarity parameter allows achieving a better Pareto trade-off, therefore obtaining higher recall for any given precision or higher precision for any given recall compared to truncation. Polarity sampling works for conditional generators like BigGAN as well. While BigGAN is trained with orthogonal regularization to allow truncation to work, Polarity requires no specific training constraints or architectural designs. It works for all deep generative networks, for example, even with ProgGAN or NVAE, as we have presented in the paper. As a byproduct of the controllability achieved via Polarity, we can obtain better FID scores for pre-trained SOTA DGNs. For example, for StyleGAN2 trained on FFHQ, we can tune the polarity parameter to improve FID. By tuning the quality or diversity of state-of-the-art deep generative networks like StyleGAN2, StyleGAN3, and BigGAN, we are able to increase the FID of these models without any retraining. Since Polarity is a plug-and-play method, it can be used with any deep generative model, even diffusion models, to control the generation and even improve the FID. Polarity sampling allows us to gain many insights from generative models. For example, polarity sampling is the first method that can provably sample from the modes of a deep generative network using negative polarity values. Via polarity sampling, we can also assess how similar the modes are to training samples. For example, in the paper, we show that VAE modes are significantly closer to training samples compared to GAN modes. Mode sampling has many possible applications, for example, quantifying the privacy characteristics of generative model across different architectures and different training regimes. So why does polarity sampling work? Polarity sampling is grounded on the spline theory of deep generative networks. Deep generative networks with piecewise linear nonlinearities like ReLU and leaky ReLU are affine spline operators. That is, it induces a partitioning of the input space and maps regions of the input space affinely to the output space in a piecewise fashion. To perform polarity sampling, we therefore do a Monte Carlo approximation of the scaling induced by a deep generative network. The scaling gives us the analytical density distribution for a pre-trained generator, and we therefore reverse engineer the analytical form to design novel latent space sampling distributions that allow us to concentrate the output towards the modes or the anti-modes.